Yeah, so hi everybody. So I'm Masaki Ando of the University of Tokyo. So I'm sorry, we had a little trouble because of myself on the host issue. So please wait a moment. But before that, yeah, I would like to announce about the Q&A sessions. So if you want to unmute and ask questions, please write it down to the Q&A part. And yeah, so I will call you. And if you don't want to speak, please write it as it and or post the question anonymously. It's okay. So maybe Luca, are you there?
Yes.
So you are now have a host. So please
okay.
give it that authority to me.
So I have to take some action from my side. I don't know.
So in the participant list, you can click my name and please give me that host authority. Yeah, thank you very much.
Okay.
Yeah. And yeah, maybe we can start. So the first speaker is Raphael, and he will talk about the hunting of binary black hole as multi-messenger sources. So please prepare for your presentation.
Yes. I guess you can see it, right?
Yes. Yeah, we can see the screen. Yeah, please start.
Okay. Well, thanks a lot. Thanks to the organizers for giving me the opportunity to present this work. I'm Raphael Mignon-Risse. I'm a postdoc fellow from the French Space Agency, and today I will be presenting the work that we've been carrying in our team with my collaborators here, and with in particular Peggy Varniere, who will be giving you a talk right after me. And this work is meant to try to predict in the future the multi-messenger signatures from accreting binary black holes. And in this talk, I will mostly actually focus on the electromagnetic part, which is, let's say, the first step towards studying binary black holes as multi-messenger sources. So first of all, why do we need co-detection in electromagnetic signals and in gravitational waves, and what do we need to perform such a detection? Well, naturally, since black holes do not emit light, we need them to be embedded in a gas-rich environment. And based on galaxy evolution theories, we think that most galaxies host a supermassive black hole at the center. Galaxy merger is a classic step in the history of the universe, so that actually every time two galaxies merge, the two central supermassive black holes should merge, but more importantly, they should merge in a gas-rich environment provided by the two host galaxies, so that there should be some electromagnetic counterpart to the gravitational wave signal. Then what would we learn from a co-detection in gravitational wave and electromagnetic light? Well, I mean, we can tackle several problems of fundamental physics, cosmology, and astrophysics. Just to mention two of them, we can actually compare the arrival time of the photons and the gravitational wave and test the speed of gravity compared to the general relativity expectations. And we could also, for example, if we could detect the system prior to coalescence and follow it with electromagnetic facilities, we could even, for example, witness the activation or reactivation of an active galactic nucleus, which would be amazing. In about 10 years, we will have the LISA space-based detector that will be actually sensitive to the frequency band of the gravitational wave emitted prior and during the merger of two supermassive black holes. And LISA will give us an error box in the sky, and the size of this box will shrink as the system approaches the merger. And the question for the electromagnetic mission of your choice, for example, the Sydnor or the Rubin Observatory, will be to try to identify, to detect, and to identify the binary black hole that we are seeing with LISA, and in particular to be able to distinguish it, to distinguish the binary black hole detected with LISA from any other source, in particular from any other transient source, such as an AGN. And to do that, we basically have to know how this accretion occurs onto those pre-merger binary black holes. So to tackle this question, I'm using the fluid code GR-AMAVAC, which allows me to follow the evolution of a fluid in a curved spacetime. And the natural question is how to treat the gravity from the binary black hole. So the simplest approach and the cheapest one would be to use Newtonian gravity. Is cheap so that actually you can follow the system for very long time scale and have a good idea about how the fluid evolves. But there are two problems. First, we know that it's not accurate close to the black hole's horizon, but also if we want not only to predict the behavior of the fluid, but also its observational properties, therefore we need to follow the trajectory of the photons from the fluid to the observers. And as we know, well, in GR, photons are deflected by a curved spacetime, so that it's an effect that cannot be taken into account in Newtonian gravity. I mean, on top of more effects coming from GR. So if you want to take the other approach, which would be the most extreme one, actually you solve the Einstein's equation so that you have from your binary black hole and your fluid, you have the metric at each time step of the simulation, but it's so computationally expensive, then you can actually run the simulation for very short time scale, probably too short. That we have adopted a third method, which is actually to implement an approximate and analytical binary black hole spacetime into our GR-MHD code. So if you are interested in this, you can take a look at this paper. Just to show you what it looks like, this is one component of the metric. So as you can see, it's quite ugly. It's just to compare it, for example, with the Schwarzschild spacetime, you would have only this term. Here you have all these terms just for black hole 1 and the same for black hole 2. So it's quite complex, but it's still less computationally expensive than solving the Einstein's equations. So I will show you the results that we obtain when using such a binary black hole metric. So you have the two black holes here orbiting at the center. We used a circular orbit approximation to begin with, and I will show you the evolution of the gas from the circumbinary disk. So we see that it forms a cavity, a low density cavity. It forms spiral arms and streams, and very importantly, after some time, it actually forms a strong asymmetry that you can see here, which is called the lump in the literature. So those three main features, cavity, streams, and the lump, they were already seen in the literature. But I want to draw your attention on this lump because actually we think that it could modulate the electromagnetic flux as it orbits, and actually it's very not understood so far. So I will just focus your attention on what could cause this lump. And one way to tackle the problem is already to see that the lump, which is an asymmetry, forms even when the mass ratio of the two black holes is 1. So that you basically have two black holes that are not distinguishable one from another. You have an axisymmetric disk to begin with, so there is a natural m=2 symmetry that you should conserve in principle. But then at some point you end up with this strong m=1. That's very surprising, and that's one of the reasons why the lump is not very well understood so far. So we did a bit of work on this, and to study the lump formation, we have computed the Fourier transform of the surface density as a function of time. And what you can see is that there is a natural m=2 all along the simulation. That's expected. That's the native mode that you expect. But then you also see an exponential increase of an m=1 that in the end dominates and is visible as the lump feature. And what the exponential increase of this mode suggests is that actually it could be related to the development of an instability at the edge of the circumbinary disk. If you are interested in this, you can take a look at this paper. Why it's important? Well, because if the lump has a strong role on the observables from circumbinary disks, we need to know the conditions under which it forms, and in particular, what is the parameter space, the region of the parameter space for which it forms. And what this scenario predicts is that actually the lump should develop for a wide range of mass ratios and orbital separation, or equivalently time to merger. Okay, so now we have a bit more physical insights onto the lump formation, but my point was actually to see whether any of those three kinds of features, cavity, streams, and lump, could produce electromagnetic features, allowing us to detect binary black holes. So to do this, we have not only to study the fluid simulation, but also to compute the synthetic observations from it. And to do this, we need a general relativistic ray tracing code. So that we have been using the Giotto code to produce these synthetic observations. Giotto with the same binary black hole approximate metric, because naturally it will have an effect on the trajectory and the frequency of the photons. And the pipeline that is formed by our fluid code and the Giotto code, the GR ray tracing code, it forms our numerical observatory that we have called INOVA, for Extended Numerical Observatory for Violent Occulting Systems, which is actually the second worldwide of its kind, the first one in Europe, basically the first pipeline in Europe able to follow the fluid evolution and then the production of synthetic observations in any type of spacetime, and in particular in dynamical spacetimes. Then to compute our synthetic observations, we will assume simple thermal emission, and because so far the fluid simulations are anormalized, we need to put some physical units back, and for that we use some references based on observational results, so that for a given binary black hole mass, we have a temperature of reference. This way, we can obtain those multi-wavelength emission maps in thermal emission that you can see here, for example, with a very strong asymmetry that we expected from the fluid simulations and the two black holes here at the center. Okay, now let's see what is the impact of having a cavity inside the circumbinary disk, or in other words, the impact of not having a lot of emitting material at the center. Well, actually, you already have such an effect around single black holes. That's what we call the ISCO, the innermost stable circular orbit, below which there is no circular orbit, so that there should be a lack of emitting material. Although actually the ISCO, it's located at several times the gravitational radius, typically 6 for a non-spinning black hole. Here, the difference is that the circumbinary disk is sculpted, the edge is sculpted as typically twice the orbital separation, so that for those simulations, it's actually about 30 gravitational radii. What it means is that actually you could compute the energy spectrum of the disk around a single black hole and binary black holes, but if you put the edge of the single black hole disk away from the ISCO, you cannot actually distinguish the energy spectrum. So if I put it in another form, what it means is that actually a binary black hole could be hidden behind a black hole source whose disk edge, which you obtain from fitting the energy spectrum, is away for no reason, basically, is away from the ISCO. Naturally, it very much depends on the black hole and binary black hole mass, because several scaling laws rely on this mass. Now, second, what is the impact of having such variable features in the disk as the lump and the spiral arms? So here I show you the accretion rate through the circumbinary disk edge as a function of time. And as you can see, it's modulated at very short period, which is actually the semi-orbital period. And on the bottom, I show you the electromagnetic flux, which we have normalized by its mean value. So that actually it's a light curve which is independent on the mass of the binary black hole. It only means that depending on the mass of the binary, it will peak in different frequency bands. But the light curve itself is not dependent on the mass. And what you can see is that the modulation of the light curve is on much longer timescales than this one. And indeed, as we could expect, the modulation of the light curve is actually produced by the lump. And therefore, it's at the lump period, which is the orbital period, the Keplerian period of the lump position, which is larger than the orbital period of the binary. And just to show you a bit more on this, here is another light curve for different parameters of mass ratio and orbital separation, just to show you how universal this behavior is. And I've zoomed onto three comparable oscillations to those ones, so that we have three lump modulations. And on top of those, we have an additional modulation, a shorter one in terms of amplitude, in terms of timescales as well, which is this time correlated with the semi-orbital period. So that's really the direct impact of having a binary on top of a light curve, which is modulated by the lump. So where does this variability of the light curve come from? Is it like just a scaling of the whole energy spectrum? Actually, it's not. What changes between a low state, basically, of the light curve and the high state, what changes is that you have actually a high energy contribution that is or is not there, depending on the state where you're at. And naturally, between the two, you will have a smooth transition. So that's actually, this is what translates in the end into a modulation of the light curve. So to conclude on this work, I've presented the results that we have obtained with our numerical pipeline INNOVA, which is the first one in Europe. We have identified accretion structures that seem to be typical of circumbinary disk around binary black holes, a cavity, formation of streams and spiral arms, and the lump, but none of those was newly discovered. What changes is that now we have a model to explain the origin of the symmetry breaking and the origin of the lump, so that we can actually anticipate for which region of the parameter space it should form. And we have found that it produces, in the end, a modulation of the light curve, in particular a 2 timescale modulation, one timescale which is the semi-orbital one, and the other timescale which is the lump period. But if we want to study this further, we need to know the black hole or the binary black hole mass, because it all scales with the binary black hole mass. And one point final point I want to raise is actually, could a single accreting black hole reproduce such behaviors? So that's an open question. Thank you for your attention.
Thank you very much. So any question? So there is no question at the Q&A part. So if you have a question, please raise your hand or just unmute and speak up. So one question from myself. So in the previous page, you showed that two different spectrum. Yeah. So, but actually, in practice, we can observe one of them. So
you're saying that? Sorry.
Yeah. In the actual case, in the actual observation, we can just observe one of them, the blue curve or black curve. So is it possible to distinguish just observing the spectrum and distinguish these two?
Well, it seems unlikely because first, I mean, you will integrate your flux on even a given time scale. So I mean, you should be very lucky to get basically the exact time at which you would have the low state spectrum and then the high state.
I see.
You know, and not to be right in the middle of the modulation. So you would need several points if you want to follow actually the evolution. So in the end, it all comes back to getting the light curve.
I see. So I'm sorry. So what is the time scale of this curve? So
this one is in orbital periods, so that I show you. I've put some numbers here that would be roughly 1 kilosecond for 10 to the 6 solar mass.
I see. Thank you very much.
For our setup. So basically for this orbital separation.
Okay. Thank you very much. So any other questions? We have 1 minute or something. Yeah, if not, let's finish this talk. Thank you very much.
Thank you.
Thank you. So next one is Peggy, and Yeah, thank you very much. And the title is Among Us, how to find a binary black hole among regular supermassive black holes, SPH. So please start.
It's a single black hole, but it's sorry.
Okay, thank you very much. Sorry.
Raphael showed you what does a binary black hole looks like, and now I am basically gonna take the opposite side and see, is it possible to reproduce the same observable with just a regular black hole? And answering your question, if we only have one SED, what can we do? What can we say? So you will get the answer in here. So, but the question is, why are we searching for pre-merger binary black hole? Like gravitational wave detection will give us a sky localization, but they tend to be quite large for the earliest part of the detections. Therefore, having some idea of what a pre-merger binary black hole looks like will help us localize it faster through electromagnetic telescopes. At the same time, it will allow us to follow the gas in the late stage of the merger, and we can see how the strong and fast evolving gravity up to and after the merger will affect the dynamical evolution of the accretion injection structure. And what we can see is that the best case scenario to follow the dynamical evolution of the system from the point of view of gas evolution will be to look at lower mass of the order of 40 solar mass binary black hole, because they will have the largest evolution range. The problem is that they might not be in a gas-rich environment. And therefore, we need another way to study the system evolution. And so one way to do that is to actually look at the system at different mass and time, but when we will not look at the evolution of this one system, but look at several systems along the path we want to follow. This way, we can have access to a much earlier pre-merger system that will not be detected just 1 month before, and it will also help us to follow the evolution of the accretion ejection structure at every single one of those stages. So in order to do that, we not only need to know what are the observable of such a pre-merger system, that was Raphael's talk, we also need to check if those observable are unique enough that they could be considered the smoking gun of this pre-merger system. And so what we decided to do is we decided to look at, is it possible for a single black hole system to mimic all those binary black hole observable that you have seen in Raphael's talk? Hence asking the question, do we already have pre-merger binary black hole observation, but they were unrecognized, misclassified as an untypical single black hole system? And so in order to do that, we use the extended numerical observatory of violent accreting system that Raphael presented. And so this code allow us to study very early on, when we have a very far away large separation, and also focus on very close to the binary. And so for the rest of that talk, I will focus on this late stage of the merger, when you have a circumbinary disk. So all the rest is in other publication and work in progress. But here that talk is only circumbinary, very late stage of the merger. And so Raphael showed you that a circumbinary black hole is giving us, once you do the retracing, you see this pivoting energy spectrum and this highly modulated light curve. And so both of those are potential observational diagnostic of binary black hole. But the question is that those are also strongly influenced by the presence of the RWI, this lump orbiting at the edge of a circumbinary disk. And in here lies the problem, because the RWI is also present naturally in a lot of accretion disk, and especially around single black hole disk. And so the question here is, can we differentiate the mass distribution inside the central object purely from the characteristic of the instability? So in order to do that, we took these two simulations, the same disk, but either a binary system in the center or a single black hole. So we change the metric, but the gas is the same. And so what we see is that the early behavior of the instability is quite different. And you see that there is a strong M=2 present in the binary black hole. It's normal, it's expected. But once the instability reach saturation, which is the most probable case we will see, like it will be very hard for us to be able to see the rise of an instability. We will have to be very lucky. And so once the instability reaches saturation, not only the mode behavior is very similar, but it would be impossible purely based on those mode distribution to distinguish if we have a single black hole or a binary black hole. And so while the overall look and behavior of the instability is quite similar, we can see that there are other differences, such as the shape of a black hole. In the case of a binary, it is not axis symmetrical. Hence, if we want to compare the two systems, we need to go to the full observables and not just focus on the lump behavior in the fluid simulation. We need to add the ray tracing also because the metric in both systems will be different. And so this difference might amplify any little effect that we see in the fluids, but are not in the purely fluid simulation strong enough. So for the idea is, how can we mimic? How do we go around mimicking with a single black hole always observable from a binary black holes? So on one side, you compute the thermal emission from the circumbinary disk. We retrace it back to the observer in the same binary black hole metric. We obtain a full spectrum. We see this little pivoting of the SEDs at higher energy. But for the next step, what we do is we compute the instantaneous evolution of the inner edge of a circumbinary disk. Having the movement of this inner edge, we will then check if having a similar inner edge, but axisymmetrical disk around a single black hole of the same mass will mimic the observable that we are seeing. From there, we will also check other disk configuration masses to reflect possible constraints we will have or not have on the system. And so if we take that single black hole with basically the same disk, but axisymmetric, same mass, we see that we have a very good fit to the SEDs that we get from the binary black hole system. And it's totally negate, purely from fitting the spectrum, the need to add a binary black hole inside the system. One of the problems that this fit gives rise to is that we need to find an explanation for the truncated inner disk. And if we have more than one observation, how does that disk is moving in time? So that is one of the problems. To lift that issue of this moving truncated inner disk, we can impose the fit to have a disk at its last stable orbit, which will probably be the first thing that someone fitting an energy spectrum will try. And so we change the mass of this single black hole to mimic the emission of a binary black hole further away. And once again, this more massive single black hole system do provide a good fit. If you only have that, you will not need to put a binary black hole. Here, you might have some tension because you see that the mass here is between 2 or 3 × 10⁷ mass, depending on what time you're observing the source. So if we have a good enough mass constraint, we might be able to say that this one has a problem. And there might be enough tension in the model. If we have several observations at different times, the mass might not be compatible with what would be accepted. In that case, we would still be left with this moving truncated inner disk. And we cannot, purely based on SED, refute the model of a moving truncated disk. So Raphael also showed that one of the stronger effects of the LWI was the creation of this beautiful light curve. Here I zoom only on one of the light curve, like very zoom, so that it's easy to see. And so the LWI happened at the edge of star disk. And so we decided to check how does, taking another simulation, single black hole, RWI, if we take the same mass truncated disk to be at the same position, or if we take a more massive black hole and use a disk at its last stable orbit, what does the light curve of WOOS, how does it compare with the one from a binary black hole? And what we see is that the light curve are compatible within 1% of one another. And which means that if you have a model through the RWI for this modulation, you do not need a binary black hole. Of course, this is a model-dependent variability. The first thing you do if you have a variability might be to use a sinusoid fit. So this is the residual coming from the sinusoidal fit. It's less than 1, it's 2% error. But the most important thing is that if you have this light curve, there is no need, there is no additional structure in the residual that would hint that we have a missing component from just a simple sinusoid. And so once again, using purely the timing, we can always find a single black hole system that can provide a good fit to what we find in binary black hole. Though, because we have a truncated in a disk that moves, we need to compensate the change in frequency. And so we might need to also have this change in mass or the change in inner disk position. Those might be possible to refute if we have a good enough independent mass estimate. But the truncated inner disk would not be possible to refute. And so it asks the question, how well can a binary black hole hide among single black holes? If you have an observation and you don't know if it's a binary black hole or not, the first thing you do is you take its spectral energy distribution, and you can find several possible single black hole systems that fit. If you look at the variability, you can also find several black holes that fit. And so neither the SED nor the variability alone can differentiate between a single black hole and a binary black hole. But what's interesting is that the mass needing for both heavy case is not the same. And so we have a hope that if we get a good independent, it needs to be independent from those observation mass estimate. As an additional requirement, we can refute the massive single black hole system, but we need to have a good independent mass estimate, and the variability needs to be modeled by the RWI. If you model it by purely a sinusoid, you do not have an add-in constraint on the mass, and this is not possible. And so in that case, we are only left with this moving truncated disk. And purely from those observations that I showed, you cannot differentiate them. But what you need is an additional constraint, and that is to take advantage of the presence of a binary period, which is unique to the binary black hole system. And if we get a high enough time resolution and a good signal to noise ratio, we will be able to detect the presence of a second, much smaller modulation that is linked to the binary period. You see that the binary period is about 1% of the total amplitude. So it will be easily swamped if we need to rebin the data or if we have a lot of noise in our data. And so being able to detect both periodicity will be a good step toward identification of binary black hole, especially if it's coupled with a good mass independent estimate. But it will still be hard to undeniably refute, because this typical light curve, characterized by a small modulation seen on top of a stronger and lower frequency modulation, is not unique to binary black hole. We have seen those, and they lie in the extension of the variability of QPOs from microquasars. Those QPOs come from instabilities, and it is very important because those instabilities creating QPOs in X-ray binaries could also be applied. All those models apply to supermassive black hole. Hence, this double variability is expected to exist in supermassive black hole. Hence, the presence of both of those variability associated with the lump and the binary period is a necessary condition for a binary black hole, but it is not sufficient for undeniable identification, at least until we improve our knowledge of QPOs in supermassive black hole system to better distinguish the variability. And just to say very quickly, can a BBH be hiding among regular supermassive black hole? And the answer is yes, they can very easily, because the slowly evolving supermassive binary black hole, when they are, say, a year or 3 years from the merger, could easily be misclassified as a supermassive black hole with some kind of quasi-periodic variability. Nevertheless, it is interesting to use this double modulation as a requirement for a binary black hole candidate, and then try to obtain a good independent mass determination that could remove a few of the possible potential model and follow-up observation with a good time resolution and low signal to noise to try to find the second modulation and have more constraint on the model. And this is just a little add at the end. If any of you have such observation of a supermassive black hole that has some kind of variability, that has a truncated inner disk, please feel free to contact us to see if a binary black hole could actually give a good fit and what type of follow-up observation would be needed to determine that. Thank you.
Thank you very much. So yeah, if you have a question, please write it down to the Q&A part or just unmute and speak up. Yeah, if not a question for me. So yeah, I'm not familiar with this area, but I have a question. So is it possible to distinguish binary black hole and single black hole from the, how to say, amount of the accretion disk? So mass or brightness or something like that. So considering that,
purely from like, if you have only one SEDs, no. Like you will always find a coherent fit to the data. If you're looking purely from, can I fit the data with a single black hole system, is yes, if you only have one observation. If you have several observations, as you see here, you will find that the system is changing. Either the position of the disk or the mass needed will change. So you might find constraint this way, but it needs to have several follow-up observations, especially those systems, if they are really supermassive, will evolve very slowly. And so you will not see them get too close. Like when they are in this kind of runaway, very close to the merger, we will see a fast variability and there we will be certain. But if we are, say, a year or two before the merger, we will not be able to do it, sadly.
Okay, thank you very much. So, any other question? So if not, yeah, let's finish this talk. Thank you very much. Okay, so yeah, let's go ahead to the next speaker. So next speaker is Ulyana. The title is focusing. Yeah, thank you very much. So please prepare for presentation. And the title is focusing detection and parameter estimation capability for different ED design in a multi-messenger context.
Yes, so hi all, I am Ulyana Dupletsa. I'm a PhD student at Gran Sasso Science Institute. And today I want to show you how we can study the expected performance of the future gravitational wave observatories, focusing in particular on Einstein telescope in a multi-messenger context. So the next generation gravitational wave detectors are expected to be able to observe a great wealth of data. For example, Einstein telescope will nominally detect up to 10 to the 5, 10 to the 6 binary black holes, binary neutron stars per year. This means that to study the performance of these free G observatories, we need to analyze entire population of events. In this context, so it is computationally unfeasible to run to use a full Bayesian approach, for example, like a Bilby software can be. So what has become like the common ground in these types of forecasts is to use a Fisher matrix approach. So here we can have an overview of the Fisher matrix codes that have been developed in recently in the gravitational wave community. And in particular, I want you to focus on this one, which is the GW-Fish, which has been developed in my institute at GSSI. So before proceeding to the applications of the code, a quick recap of what a Fisher matrix formalism is. So in the Fisher matrix analysis, we are working in the high signal to noise limit. And in this context, the gravitational wave likelihood can be approximated as a multivariate Gaussian with the covariance matrix given by the inverse of the Fisher matrix. So the Fisher matrix, as you can see here in the expansion of the likelihood function, is the scalar product of the derivative of the signal with respect to the parameters on which we want to estimate the uncertainty. In this particular studies for forecasts for the future detectors, we are using the so-called zero noise approximation, which means that we are not simulating any noise so that the first term is not taken into account. So GWFish, which is the code that we developed here, is a code entirely written in Python, and the three pillars it relies on are the waveform approximation, which is taken care for using an embedding with large simulations that we can use all the available waveforms that are present in large simulations package. Then we have the derivative part, and this one is solved partly analytically for those parameters where we can have analytic derivative, or partly numerically for all the others. And the central one, which is the Fisher matrix inversion, because this is the operation that will give us the covariance matrix, and so the uncertainties on the parameters. In GWFish is using the singular value decomposition method to invert the Fisher matrix and to take care of instabilities and the so-called degenerate Fisher matrix. So, oh, sorry. Okay, I skipped a slide. In GWFish, we can simulate different types of detectors. So we can simulate the potential upgrades of the current infrastructure. So we have the two LIGO, Virgo, LIGO India, KAGRA. We simulate the 3G detectors, which is the focus of this presentation, so like Einstein Telescope and Cosmic Explorer. There is also an implementation of the approved spaceborne detector, LISA. And we have concepts like LGWA, which stands for Lunar Gravitational Wave Antenna, which is a proposed lunar mission that wants to use the entire moon as a gravitational wave detector. What we want to do here is to study an application of a Fisher matrix called such GWFish. So, for example, we used this code in this huge work that constitutes the science reference paper for the COBA study. This work was led by Marica Branchesi and Michele Maggiore, and many scientists contributed to this paper. And this study collocates in the larger COBA study. COBA stands for cost and benefit analysis, and this represents the scientific part of a much broader work in progress, where there is a specific committee that is evaluating the risks and the costs of the Einstein Telescope project. Here is an overview of the structure of this huge work, and I highlighted the part on which we will be focusing today, which is the multi-messenger astrophysics. So just to give you an overview of what is done in this study is that we are taking the reference design of Einstein Telescope and comparing it to different designs, to different geometries and different sensitivity curves. So what we have here is that the reference design of Einstein Telescope is that of a triangular shaped 3 nested interferometers, each of 10-kilometer arms. And each arm consists of a xylophone configuration made of 1 interferometer that is tuned towards high frequencies and 1 interferometer which is cryogenic, tuned towards low frequencies. This reference design is then to be compared to different configurations, because you want to evaluate the impact on the science, on different science cases, changing the geometry. So we are comparing the triangular shape versus the 2L shape. We are using different arm lengths, and here you can have a list of what are the configurations that are being studied in this paper. And also we are taking into account the fact that maybe in the first stages of the development of Einstein telescope, we won't have access to low frequency, so we won't have the cryogenic part, and we will be left only with the high frequency part. And in this case, what will be the impact on the scientific outcome for Einstein telescope? So given these settings, we want now to focus on the multi-messenger astronomy. In particular, the objective here is to study the impact of different detector geometries, the one we saw in the previous slide, and the sensitivities on the multi-messenger capabilities of Einstein telescope operating in synergy with electromagnetic observatories. These observatories will probe the formation, the evolution, and the physics of binary neutron star systems in connection with kilonovae and short gamma ray bursts. The multi-messenger study will greatly benefit from the large joint electromagnetic gravitational wave detections that we expect from a frigid detector like Einstein telescope, and will also benefit from the greatly improved parameter estimation capabilities of ET with respect to the current detectors. The main parameter here that is determining the joint gravitational wave electromagnetic observations, and so affecting the multi-messenger performance of Einstein telescope, is the ability to localize the source and the volume of the universe up to which we will be able to detect binary neutron stars in terms of the achieved redshift. So, and another important in this scenario, what is another important aspect is the ability to localize the BNS merger before the merger itself, and so to send a pre-alert with a good estimate of the sky localization of the source. This is critical because we want to detect prompt and early emissions in the electromagnetic bands where all the sky monitors are not always operating. So we want to localize the source before the merger. Last, for this analysis, we are using a detection threshold SNR of 8 because we are taking into account that the presence of the counterpart increases the significance of the source detection. This is to say that usually the SNR threshold is higher for a Fisher matrix forecast. In this case, we are lowering because we are assuming that there is an electromagnetic counterpart. In the plots here, we can see the comparison of different designs, and we are plotting the sky localization uncertainty for all the detected gravitational wave events, and the different colors show the detections localized within a certain threshold on the sky localization, and all the sky localizations are given within the 90% credible region. As we can see here, the comparison between the different design is that the 2L15 kilometers is giving the same more or less results as the triangular shape 15 kilometers, and it is better than the 10 kilometers. This will be a pattern that we will observe also in other scenarios. And of course, if we go to longer arms to 2L interferometer, then we will have, with respect to the reference design of ET, almost 4 times the detections well localized. And with well localized, I mean like less than 10 square degrees, and we can go up to higher redshift, which is like 0.4 with respect to the reference design. And just a quick note here, when I refer to L15 or either 15 or 20 kilometers, and the arms are misaligned, so they with respect to one another detectors, they are rotated by 45 degrees. Then we can also study the, as we have said before, the impact of having or not the cryogenic part of in our detector sensitivity. So this table is to read like left, right, and top, bottom. So in the top part, we have the results using the full sensitivity curve, which means we have both the cryogenic and the high frequency detectors operating. Instead, in the bottom part, we have only the high frequency part. Then on the left, we are using all the random orientation of binary neutron stars, and on the right, we are selecting only those, the so-called on-axis events, where the viewing angle is below 15 degrees, because we expect that a percentage of these events will emit a gamma ray burst, which is supposed to be emitted perpendicularly to the orbital plane of the binary. So here, what is the outcome of comparing the full cryogenic sensitivity curve with respect to the high frequency scenario only? So what we can see is that generally, if we are taking all the orientations of binary stars, the both the 2L scenarios, 15 and 20 kilometers, are similar in this case to the reference triangular shape. But if we are saying here, in case we are losing the HF part, and instead, if we are taking only the on-axis event, we see that the decrease of events that are well localized in case we are losing the cryogenic part are in percentage lower with respect to the randomly oriented systems. And in this case, we obtain that the 2L 15 kilometers, is comparing not to the 15 triangular as in the case before, but to the 10 triangular detector. But the takeout from this study is that losing the high frequency, losing the cryogenic and having only the high frequency in general gives us much less systems to and well localized, and also at lower redshifts. This has an impact on the pre-merger detections as well. So the detection of prompt and early multi-wavelength emission from binary star mergers is critical because they are crucial to probe the central engine of gamma ray bursts. And this is particularly important if you want to understand the jet composition and the particle acceleration mechanisms. Moreover, if we detect a BNS merger signal before the merger, then we can detect also electromagnetic precursors. And we can also image the sky localization area so that we can remove contaminating transients eventually. So here, as in the table before, we present on the left all the orientation binary star systems, and on the right only those which are seen on axis. And the on-axis detection is particularly important because if we want to observe, for example, the very high energy early emission from gamma ray bursts, which so far has never been observed before. This is like a study from Banerjee et al. That has come out recently. As for the kilonova emission, on the other hand, it has been shown that the early phase emission is particularly important because it is sensitive to the structure of the outer subrelativistic ejecta. And this can give rise to the early UV emission, which can be detectable by ultrafield satellites. So what we can see from these results is that if we are focusing on the all orientation systems, then again, we have that the triangular 15 kilometer and the 12 15 kilometer misaligned give similar performance with the triangular the triangular 15 slightly better. And in this case, the triangular 15 kilometer for the pre-alerts is comparable to the 12 20 kilometers. On the other hand, if we focus on axis events, we can see that this is the similar colors, like this 10 kilometer triangle and 12 15 give similar outcomes, as well as the triangular 15 kilometer and the 12 20 kilometer. Again, if we don't have the low frequency part, as you can see from all these zeros in the table, we have a dramatic decrease of well localized events, and so we have practically no localized pre-merger detections, which is a pity if we want all the scientific outcome that we discussed before. So to conclude for the COBAR scientific paper, so what we have seen is that also, like, okay, we have only presented the multi-messenger part, but the conclusions hold for all the scientific cases that have been studied in the paper, is that all the triangular and the 2L geometries that have been investigated would make a fantastic next generation gravitational wave detector, and the improvements will be really great compared to the current 2G detectors. What we have seen is that, okay, the 20 kilometer 2L design is maybe the best, but it's unfeasible. It's too optimistic design. But the 2L 15 kilometers is the one that offers a better scientific return with respect to the reference design of 10 kilometer triangle. And as we have highlighted before, it has a similar performance as the triangular 15 kilometer. What has come out for sure is that if we don't have the low frequency, if we don't have the cryogenic part and only the high frequency, then independently of the geometry that we choose for our detector, many scientific targets will be lost. So as we have seen before, all the pre-merger alerts, and prompt emissions. And so to draw the conclusions of all this work, so what I want to highlight is that we are expecting lots of data from the next generation gravitational wave observatory. So in the meanwhile, they are advancing with the high-speed techniques for full Bayesian parameter estimation, which will be used for the next generation detector. We can do forecasts using Fisher matrix codes, and so to study how these detectors will perform and what will be the scientific return that we can get from the next generation detectors. So that is all from my side. Thank you.
Thank you very much. So any questions? Yeah, maybe it's okay to just unmute and speak up.
Hi.
Yeah, yes, please.
Yeah, so I have a small minor question. So the localization value you quote comes from the Fisher matrix approximation, right?
Yes.
Yeah. So do you incorporate the mass parameters, or you just only during the Fisher matrix, or
yes,
just
so all the 15 parameters are incorporated. So in this case, we are not considering spins, but we are considering tidal deformabilities. So it's 9 plus, yeah, it's 11 parameters that we are incorporating here.
Can I ask a small question?
Yes, sorry, not 11, 13, because you are considering the spin magnitude, but not the other angles of the spins. Yes, of course, go ahead.
Yeah, so since you are also one of the detector is tuned for the low frequency, so did you consider the subdominant mode of the waveform, or consider only the dominant 1, 2, 2 mode?
Here we are considering the IMR phenom D tidal waveform approximation too.
Okay, thanks.
Thank you very much. So Arvid, go ahead.
Yeah. Hi, Ulyana. Just a question. So can you go back to slide 11? Because I mean, there you showed the results for the, I think it was a population of neutron star. Maybe I missed that.
Yes, it's a BNS population.
Okay, so basically you have localization smaller than 10 square degree up. Okay, to really low redshift. Okay, which means that then in the number that you're reporting in the next slide, okay. So here is just on the GW side. I mean, there is no requirement on the detectability of the electromagnetic counterpart, or since they are all close events, you're just saying that, I mean, you can detect everything.
No, these are, sorry, I think I misunderstood your question. So you're saying if we have put some filters on these results?
Yeah, exactly. Or is just on the GW side?
This is just on GW side, so we are expecting that, for example, on this right part, that a fraction of that will produce eventually a short gamma ray burst, but we are not assuming that which percentage is producing gamma ray burst. So this is just gravitational wave analysis.
Okay. But I mean, since they are all close by events, I mean, especially the one localized with the delta omega 90%. Okay, yes, for the ones smaller than 10 square degree, they are all close by events.
Yeah, because if you see here, like smaller than degrees, it's this violet part. Yeah, so it's it goes to up to 0.4 only if you're considering this geometry.
Okay, and maybe just a last question. Quick, you mentioned about the fact that you also have LISA in GW fish.
Yes.
Can you say something? I mean, how it's implemented LISA?
Yeah, so we are using a different coordinate set, the solar centered coordinate set, and we are using all the the free channels for the sensitivity. So it was I think AT and E combined, for to describe the sensitivity.
Okay, wow, cool. Yes. Thank you.
Okay, so Waratkar, please.
Okay, my question is, you compare here these two different designs, the triangle and the 2L in their multi-messenger capabilities. But my question is, like, how would these compare in, for example, other practical aspects? Like, do you have any idea? Would one be easier to construct than the other? Would one be cheaper than the other? Or they're all comparable in that regard?
Okay, so they are not comparable because you have to estimate what will be like the excavation volume for to construct the triangular or the 2L shape. So then also so in this case the 10 kilometer triangle, so you have to take into account that there are 6 interferometers actually, because if you see the shape, so you have to account for not only the length but also for the volume that you have to excavate. And for the costs, like what will be the difference between like the triangular shape and the 2L, this is being evaluating in these years, and also like where the Einstein telescope will be built, if it be the triangular configuration, or if we will have the 2L. In this case, it will be in 2 different states.
Okay, thank you.
Any other questions? Yeah, if not, yeah, let's finish the talks. Thank you very much. So we will have a short break, and we will restart from 10 minutes after now. So see you later. Hi, welcome back. So it's almost a time to restart. So yeah, Luca, please prepare for your presentation. Yeah, thank you very much.
So, hi all, I'm Luca D'Onofrio, researcher at University of Naples, and in this presentation I will describe the latest results by the LIGO-Virgo-KAGRA collaboration about the targeted search for continuous gravitational waves from known pulsars. So this is a kind of signal different from the one that we have seen so far by the previous talks, and as you can see here, there are the sketch of the 4 different main group of sources that we. Sorry?
Yes.
Yeah, please go ahead. Okay.
So continuous signals are long-lived signals. The time scale is of the order of months or even years, with a well-modeled, well-known waveforms. And for ground-based detectors, the main sources for this kind of signals are isolated spinning neutron stars with a non-axisymmetric mass distribution. Continuous signals at the source are almost monochromatic, with the gravitational wave frequency that is proportional to the source rotation frequency. But the amplitude of this kind of signals is expected much weaker than the one that we have, for example, detected from the merger of black hole or neutron stars. And in general, 8 parameters can define a continuous signals. 4 extrinsic that are linked to the source, and that are the rotation frequency, how this rotation frequency changes in time, and then the sky source position of the source. And then 4 intrinsic parameters linked to the gravitational wave, that are the amplitude, the phase, and then the polarization parameters. Now, according to our knowledge about the extrinsic parameter, there are different strategies for the analysis of continuous signals. And the topic of this presentation is the so-called targeted search, that, as you can see from this plot, where there is on the y-axis the sensitivity of the analysis as a function of the computational cost of the analysis itself. Targeted searches are the most sensitive analysis that we can perform for continuous signals, since in this case we assume to know with high accuracy the rotational parameter and the sky position. So in other words, we assume to know very well the source. And in this case, the targeted searches are also the less expensive in terms of the computational cost of the analysis. Then you can relax the assumption on the source, and then you start to explore larger parameter spaces. And so you need to consider different kind of analysis, and the sensitivity of this analysis decreases with an increasing of the computational cost of the analysis itself. Of course, since you need to know with high accuracy the the source parameter, the targets are pulsars for the targeted search, because you need an independent and so an electromagnetic observation of the source, because you want to constrain the extrinsic parameter. And so pulsars are spinning neutron stars that are observed in the radio, in the X-ray, and the gamma ray band. Up to now, we know almost 3,000 of known pulsars, and this is only a small fraction of the expected number of neutron stars in our galaxies. And since we know the extrinsic parameter, we also know the shape of the signals over for example, long time scale. And so we can use full coherent method. And so for this reason, the targeted searches are the most sensitive analysis that we can perform. And in the context of the LIGO-K collaboration, we have 3 pipelines for the analysis of these signals, the Bayesian method, the F statistics, and then the 5-vector method. And of this last pipeline, I will describe some details in the next slide. Then why to perform analysis for this kind of signals? Well, up to now, we have no detection of continuous signals, but a future detection can return important information about the physics of the neutron stars, for example, about the equation of state. But of course, this depends on the emission scenario that we want to consider. And the simplest model that entails emission of a continuous signals is the so-called bumpy neutron star model, in which the solid crust of the neutron stars has a small deformation. And this deformation entails emission of a continuous radiation with the gravitational wave frequency that is exactly twice the rotation frequency of the source. And here you can see an expression for the expected value of the amplitude, that is of the order of 10 to minus 27 in terms of strain, of course, fixing the gravitational wave frequency, the distance, the moment of inertia, and a value of the ellipticity of 10 to minus 6. The ellipticity is the degree of the deformation of the neutron stars that is typically approximated by the ratio between the deformation of the radius of the neutron stars and the radius itself. Now, generally, a radius of neutron star is of the order of 10 kilometers. So a value of the ellipticity of 10 to minus 6 means that the deformation of the radius that we are looking for is of the order of the centimeters. Then we can also set a theoretical upper limit on the expected amplitude, because we observe in the electromagnetic counterpart that pulsars spin down. And so we can assume that this spin down of the pulsars is completely due to the emission of gravitational wave. Of course, this is a strong assumption, but it allows to set a theoretical upper limit on the amplitude, that is the so-called spin down limit. So in the bottom part of the slide, you can see a sketch of the signals, because at the source, I would say that the signal is almost monochromatic, but we have to take into account the spin down of the pulsar, so the decrease in the rotation frequency. But then since the detector is on Earth and the Earth is traveling around the sun, we have also to consider the Doppler effect due to the Earth motion. So you need to correct for the Doppler effect and of the spin down. But after this correction, there is a residual modulation due to the sidereal motion of the Earth. And then there is, at the end of the day, the detector noise that, of course, complicate the analysis. Now, to correct for the Doppler and the spin down, we use a demodulation technique that is called the heterodyne method. The starting point of this correction is a complex and already filtered and subsampled data, the so-called band sample data files, that allow also to reduce the computational cost of the analysis, because you only consider a small frequency band around the expected gravitational wave frequency. And then you multiply these starting data with this exponential factor, in which you reconstruct the modulation of the phase due to the spin down, as I said, but also due to the Doppler effect, due to the Earth motion, and also if the pulsar is in binary system, and this happens in most of the cases that we analyze. We have also to consider the motion of the pulsars in the binary system, and so there is a different contribution term linked to this Doppler effect. So then if you, after the correction of the spin down and Doppler effect, there is the residual modulation due to the sidereal motion of the Earth. And these this modulation split the signal in 5 frequencies. You can see this splitting clearly in this amplitude spectral density for one of the LIGO detector during the last observing run. And of course, this is a clear signal, but it's what we call an hardware injection. So we move the mirror of the interferometer to simulate continuous signals. In general, hardware injection a strong signal-to-noise ratio, and they are commonly used to test our pipelines, as in the case of this hardware injection. And you can see that the central peak is at twice the rotation frequency for this particular hardware injection. And then there are 4 sidebands with the distance from the central peak that is proportional to the angular sidereal frequency of the Earth. This splitting in 5 frequency is the core of one of the data analysis pipeline that we use in the LIGO-Virgo-KAGRA collaboration, that is the 5-vector method. This method has been developed in the last 10 years by the Rome Virgo group. And it is based on the computation of the so-called 5 vectors. For example, here are indicated in bold. This is the data of a vector, and these are the template of a vector. The data of a vector is a vector with 5 components, and each of the components is the Fourier transform of the output of detectors in each of the 5 frequencies where the signal is expected. And the same is for the template 5 vector, but instead of the output of the detector, you have some functions that are proportional to the antenna patterns. And then the 5-vector method is basically a matched filter in the frequency domain. So you can construct this 2 estimator, taking the scalar product between the 5 vectors. And then in a frequentist way, you can compute the detection statistics, and then, for example, compute the p-value or upper limit in case of no detection. Now, in the next slide, I will describe the latest results for the targeted search by the LIGO and Virgo collaboration. For this paper, I worked as an analyst in the editorial team. We have analyzed the 236 known pulsars using the data from the LIGO and Virgo detectors and the last observing run and also the O2 run. We have considered a single harmonic scenario, that is the bump neutron star model that we have seen before, but also a different emission model, that is the dual harmonic model that entails a gravitational wave at rotation frequency and at twice the rotation frequency. For all of the 236 pulsars, we used the Bayesian method to analyze these pulsars, and then the F statistics and the 5-vector method only on a subset of these, in the so-called high-value pulsars, that are the pulsars with an experimental upper limit below the theoretical upper limit. And we have found no evidence of a continuous signals from any of these pulsars, and so we set upper limits on the amplitude and with an estimation of the distance also on the ellipticity of the pulsars. And the results can be summarized in this plot, where you have on the y-axis the let's say the upper limit on the amplitude as a function of the expected gravitational wave frequency. Then here, the blue stars are the experimental upper limit with the Bayesian method. The gray triangles are the theoretical upper limit, the spin down limit, while the solid pink line is the expected sensitivity for our detectors. And as you can see, only for almost 23 pulsars, we have an experimental upper limit that is below the theoretical spin down limit. And let's focus also on the case of these pulsars, in which with an estimation of the distance of 0.1 kiloparsec, the upper limit on the ellipticity is of the order of 5 times 10 to minus 9. This means to constrain the deformation of the radius, or in other words, the mountain on the crust of the neutron stars that is below 30 micron. And in this last slide, in this paper that has been submitted to PRD, I described also the first application to the 5-vector method to pulsars in binary system. So we recently have developed the Doppler correction for pulsars in binary system for this method. And on the plot on the left, you see the comparison between the 5-vector results that are the red circles here for the upper limit of the amplitude, of course, that are compared with the Bayesian upper limit that we have seen before. And on the right, there is the histogram of this normalized difference to compare the results from the two different pipelines. And as you can see, this is almost peaked at 0, as you expect. And so to conclude, known pulsars are promising sources for continuous radiation. In the context of targeted searches that are the most sensitive analysis that we can perform, there is a strong multi-messenger approach because you need to constrain the extrinsic parameter, because in other words, you cannot use full coherent method if you don't measure the extrinsic parameter from the electromagnetic observation. And latest results from the LIGO-Virgo-KAGRA collaboration show no evidence of a signals from any of the analyzed pulsars, but we can set interesting upper limits. For example, for 23 out of the 200 pulsars, we set upper limit on the amplitude that are below the theoretical spin down limit. And then I also shown the first application of the 5-vector method to pulsars in binary systems. And so now we have a new method to analyze all the pulsars that we consider. So thank you, and let me know if you have a question.
Thank you very much. So any questions? Yeah, please unmute and speak up or raise your hand. So yeah, I have a question from myself. So you mentioned about the upper limit for the electricity. So is it consistent with so how to say magnetic field of the pulsar or something?
Is it? Sorry, can you repeat, please?
Is it consistent with the other constraint coming from the magnetic field of the pulsar or something?
No, sorry, can you repeat, because I didn't understand.
So you mentioned about the mountain, but actually the pulsar will be deformed by the magnetic field by itself.
Oh yes, the deformation of the crust is only one possible explanation of the deformation of the radius, but there are other possible let's say theoretical explanation for to have a non-axisymmetric deformation of the neutron stars. For example, linked to the magnetic mountain, or of course the so-called R modes, so the oscillation in the crust of the neutron stars. But of course you have a different emission model, and so also a different signature in your data. So for example, these are possible different models, as you can see from the dual harmonic search. And this is if you have a superfluid component in the interior. So if you have a solid crust but a different interior that moves in different wave, you have a dual harmonic search. But the case if you have a wobbling neutron stars and so on. So yes, it depends on the theoretical model for the non-axisymmetric deformation.
Okay, thank you, Brad. So yeah, Ulyana. Yeah, please go ahead. Can you speak? Yeah.
Oh, I'm sorry, I was muted. Yeah, so I was saying thanks for the nice talk. I was wondering, when you use these multiple pipelines for the high value pulsars and you get upper limits from the different pipelines, do the upper limits compare well the way you expect them? So do the upper limits look similar from the three pipelines?
Yes, in the hypothesis of Gaussian noise, we expect that the upper limits on the amplitude are similar. And this is what happens here, for example. Now in the LIGO-K paper, we just used the other two pipelines in a small subset. But you can see, for example, here with this new analysis for using the 5-vector method in all the set of 200 pulsars, and the results are really similar. Okay. Of course, there is a small variation, but it's linked to the random noise. No.
Right. Also the upper limits.
And, yeah. Also, sorry, excuse me. Also, it depends on different framework that you use.
Yeah.
So, for example, we use the band sample data framework, but the Bayesian analysis uses a completely different framework.
Yeah.
And so the difference in the upper limit can be explained with these differences.
Right. Okay. Thanks.
You're welcome.
Thank you very much. So, any other question? We have 3 minutes left. Yes, please go ahead. Idea.
Yeah, thanks, Luca, for a very nice talk. I just wanted to ask you about this. For targeted searches, you consider a very long coherence time because you can afford
Sorry?
Do you consider very long coherence time for these targeted searches? So,
yes.
For long coherence time, your signal your search can be very sensitive to some intrinsic deviation from your expected signal, right? So do you approach it in a hierarchical way where you consider different coherence time, or is it just done with one set coherence time that you have for your?
No, it's just for one coherence time. We take the entire observing run. We consider an emission model, a theoretical emission model, and then we look for a signature in our data. Then this is of course the case of targeted searches, but of course you can consider different analysis. For example, narrow band searches. When you consider when you take the sky position with high accuracy, but you allow a mismatch between the gravitational wave frequency and the rotation frequency. And so you look for a small frequency band around, let's say, twice the rotation frequency. And so in this case, you are, we don't know precisely the emission model. And so we look for a different frequency. But of course, this is a different kind of analysis because you take a parameter space that is equal to the frequency band that you want to select, and then you have a trial factor to consider. So for this reason, the sensitivity decreases.
Okay, thanks.
Thank you very much. So is there any glitch during the observation run for these 23 pulsars?
Is it?
Is there any glitch of the pulsar during the observation?
Oh no.
No.
Okay, glitch. Okay. Yes, there are glitches for 2 pulsars, if I remember well, and also the grab, but I have to check. But the idea for glitches, because for example, let's say that the pulsars glitch during O3. Then you have a rotation frequency before the glitch and the rotation frequency after the glitch. The common idea is to independently analyze the first part, so before the glitch and then after the glitch, and then coherently sum the statistics. This is the method that you can use.
Okay, thank you very much. So, any other question? Yeah, if not, thank you very much.
Thank you.
Yes, so let's go ahead to the next speaker. So, yeah, next speaker is Otto, and the title is Localizing Merging Black Hole Using Gravitational Wave Lensing. Yes, we can see. Yeah, thank you. Go ahead. Yeah, please go ahead.
Okay, perfect. Well, first of all, thanks a lot to the organizers for setting this up. I think it's very nice to see Amaldi in full swing. So just to introduce myself, my name is Otto. I'm an assistant professor at CUHK in Hong Kong, working on gravitational waves. And my talk is going to be about this idea that we've discussed kind of over the years regarding localizing merging black holes using gravitational wave observations together with lens reconstructions. So within this talk, since I know that most of the people here are more on the gravitational wave side of things, I'll try to sort of introduce the idea primarily and some of the kind of key concepts that go into it. So before we can sort of get started with the main topic, I want to answer 2 questions. The first one is, what is gravitational wave lensing? And the second one is, the simpler question, which is what is gravitational lensing? And so the history of gravitational lensing goes back all the way to 1915, I would say, when Albert Einstein, so this handsome gentleman on the top left, formulated his theory of general relativity. And one of the consequences or predictions of general relativity is that massive objects bend light rays, which results in gravitational lensing. So that was a prediction that was confirmed in 1990 by Sir Arthur Eddington. And it was the first time that a prediction of GR was confirmed. And so it essentially made Albert Einstein a household name. So since then, there was sort of a very quiet period when it came to gravitational lensing in 1936. Mandel paid visit to Albert Einstein and sort of encouraged him to write a paper on lensing by stars, where he sort of noted very quickly that this lensing is probably something that is going to be very difficult to see. But then 1 year later, Fritz Zwicky sort of picked up this work and suggested that gravitational lensing actually could happen for not lensing necessarily by stars, but by lensing by galaxies. And he made a lot of predictions about what kind of lensing might happen in the future. And in 1979, so 4 decades later, there was the discovery of the first strong lensing system. So what you can see here is an example of a single quasar that is being strongly lensed into 2 images. And then 1 year later, there was a discovery of the lensing galaxy that actually produced these lensed images. And since then, gravitational lensing has become an observational tool. And now today, 4 decades later, I think it's fair to say that gravitational lensing has grown from a sort of an abstract tool into a standard tool set in the study of the cosmos with a rich number of science applications. So besides the prediction of GR that massive objects bend light rays, similar phenomena, so gravitational lensing should happen also for gravitational waves, where there's been a significant number of effort to build the tools to detect and analyze gravitational wave lensing in the recent years and build the science case around it. So within this talk, I'll be focusing on just strong gravitational wave lensing in the geometric optics limit. But I'd like to maybe highlight that there are also other interesting lensing talks in Amaldi who are maybe interested in the broader gravitational wave lensing research. All right, and so with that sort of out of the way, I want to ask the next question, which is what is strong lensing and how do we actually observe it in gravitational waves? So in the traditional astronomy, it's sort of easy to answer, what strong lensing is and how we observe it. We would see, for example, here's an example of a lensing galaxy that is splitting a background quasar into 4 multiple images. So that's an example of strong lensing, which produces multiple images. And so you might, we might expect that with gravitational waves, we should be able to see something similar, but instead of a quasar, there should be binary black holes that are being multiply imaged. But the key point is that the image separation between these multiple images is of the order of arc seconds. And so that means that with, for example, the current gravitational wave detectors, it's quite difficult to resolve these images because the sky resolution is not good enough for that. And so instead, there are efforts to detect strong lensing, not as these multiple images, but as repeated events. So instead of seeing them as these images, what we would see is each image arriving to us at different times with different magnification and different overall Moore space. And so when we say what is strong lensing and how we observe it, would be observing the same phenomena but differently in gravitational wave detectors. Right, and so since the presentation is focused on kind of this idea of how you can actually, how you could localize merging black holes using gravitational wave lensing. And so I want to sort of give the rough sketch of the idea first. So the basic assumption is that we have localized or we have seen a gravitational wave that is strongly lensed. Say there are, for example, 4 images. And the interesting part is that the first step after this kind of detection would be to analyze the image properties of these gravitational waves. So by image properties, that's a sort of shorthand from my own terminology to talk about the magnifications, time delays, and the Moore spaces, or the effective luminosity distance to Moore spaces. To measure the image properties to learn something about these images. The interesting part is that those images can be mapped to a gravitational lens model as well. And so essentially these gravitational wave images, they carry some information about the strong lens that produced them, and it allows us to rebuild the strong lens to some degree of accuracy. The first thing that is interesting about strong lensing and observing these repeated events is that they allow for us to effectively increase our detector network. And so when we see gravitational wave strong lensing, we've seen the same binary black hole multiple times, and effectively we have a larger detector network. And this is interesting because a larger detector network allows for better gravitational wave sky localization. And this was something that was already discovered in 2004 by Seto et al. And so when we say the idea is to localize merging black holes, then the sort of idea from here is to try to observe this sky patch, the gravitational waves in the electromagnetic band. And sort of as a very rough illustration, you might be able to see something like this. So what is in here is galaxies and strongly lensed galaxies. And there is another key assumption that we can make when it comes to strong gravitational wave lensing, which is that if the gravitational waves from the galaxy are strongly lensed, then we would expect that the light from the galaxy should also be strongly lensed. And so when we want to ask, which galaxy did the gravitational wave come from, we expect binary black holes to reside in galaxies. Well, we can translate that question to is which strong lensing system does the gravitational wave come from? There's about a factor of 1,000 reduction in the number of galaxies that we would need to search for by doing this. And then there is one more key component, which is that if we have an understanding about the gravitational lens, then combining it together with electromagnetic information, we can try to cross-match what we see in the gravitational waves with what we see in the electromagnetic band. And so the rough idea would then be to say, if we can find a match for it, then we've localized the gravitational wave down to the correct galaxy lens system. So how does this work in practice, and what are some of the important questions, or a subset of the important questions? So some of the kind of gravitational wave questions that we can answer regarding sort of practical feasibility of this is that we should have an understanding of how well the gravitational wave source can be localized in the sky. Because if it's, for example, 1,000 degrees squared, it will limit some of the electromagnetic capabilities, versus if it's a 1 degree squared, it's easier to search for. Another question is, where do the search originate from? So if the lens gravitational waves come from very far in the redshift, it will be more difficult to actually observe the electromagnetic lens system. What kind of lens system produced the gravitational waves? So whether or not it's a larger or more massive lens or a smaller one is another important question. And then finally, what does actually combining some of this multi-messenger information bring to us? So answering the first question regarding the gravitational wave sky localization, what we did was carried out parameter estimation with a few hundred gravitational wave events that were strongly lensed and quadruply lensed. And we arrived at this sky localization of about 10 degrees squared, roughly, which is reasonably good for a wide field of view survey. This, of course, depends a little bit on the signal-to-noise ratio, and there have been some further improvements to these results from incorporating joint parameter estimation that were already included in this original work. So where do the sources originate from? They come from roughly redshift of 1 to 4. This is interesting because a lot of the electromagnetic instruments like Euclid may be able to see up to redshift of probably 2 or 3. And so they sort of coincide with what you might expect from electromagnetic observations. And then how likely can we find the lens? What we did here was we simulated a set of gravitational wave signals and lens systems. I believe that there was about 530 lens system here, produced by a massive lens, intermediate mass lens, and low mass lens. I believe the massive lens was few arc seconds, 1 arc second, and 0.3 or 0.5 arc seconds. And what we wanted to figure out is, can we actually disentangle the gravitational wave or the correct host galaxy from the background? What we find here is that with ground-based imaging, it may be quite difficult, but with high-resolution imaging, like the HSD, things get better. So that's one of the interesting findings here. This is the correct ranking statistic, whereas this is the background. And it also gets easier with more massive lenses instead of intermediate mass lenses or low mass lenses. And this is because of the rarity of more massive lenses. So there's some further follow-up work. So we didn't include all of the joint parameter estimation and kind of joint analysis in this framework. So we have some further work going on into kind of quantifying some of the improvements from some of the other techniques that we intend to look into. And the last question was that we wanted to look into was what information does multi-messenger modeling of these strong lensing systems provide? And so what you can see here is a HSD like imaging of a typical strong lensing system, and we jointly modeled the gravitational lens and the source system using electromagnetic and gravitational wave measurements. And one of the interesting things is that it seems that after deconvolving the source or after reconstructing the source galaxy, that it would be possible to pinpoint where the merger happened down to sub-milli-arc second position. There are two technically other questions that I'll sort of postpone to other talks, which is how well can we actually model gravitational wave lensing, using gravitational wave data or electromagnetic data. But I think the short story is that by incorporating some of the electromagnetic information in our analysis, the lens modeling improves. And for that, there's going to be a talk on Saturday by Jason Poon. So he'll talk about that more in detail. And there was work by Ewald Wempes, or one of the actually master student from Groningen, looking into sort of the practical identification probabilities in Euclid, where we reached a number of around 20 to 40% of the events being possible to identify statistically and correctly with Euclid. Right, so that's the rough idea that I wanted to introduce. And I'll just summarize this by saying that strong gravitational wave lensing may allow us to do localization of merging black holes down to the host lens system. And the idea follows from the fact that these analyses allow for better sky localization, and this assumption that that you will be searching for only strongly lensed galaxies, and that we can reconstruct the gravitational lens in EM and gravitational waves. And then post-identification, there are interesting science cases that could come out of this. Right, so let me just say a couple of words about the future directions and benefits, and then I'll post the presentation. So some of the potential improvements. So on the gravitational wave side, one of the things that we're currently working towards is understanding better the sky localization aspects using joint parameter estimation. And there's some work that needs to be done in improving the lens inversion algorithms and looking into the role of so-called sub-threshold lensing searches to see if these could help with the localization. And on the EM side, I would say that some more statistical studies with different instruments and telescopes, I think, will be necessary to see how this idea pans out in practice. And in terms of the benefits, I would say that this would allow for localization of merging black holes that don't have electromagnetic counterparts, and it will allow us to localize the merger within the host galaxy. And this may be interesting from the gravitational wave perspective or the gravitational wave lensing perspective, in terms of improving some of the the existing science capabilities, or in terms of some of the new science opportunities. There are a couple of interesting follow-up papers, for example, modified gravity applications of this work. So thank you very much for your attention, and I'll be happy to take questions.
Thank you very much. So any questions? Yeah, please unmute and speak up. Yeah, so a question from myself. So if I miss something, I'm sorry, but are you using the information of the time difference between waveforms?
Yes. So what the information that we're folding in is all the gravitational wave image properties. So in this case, it's the time delays, the amplitudes of the gravitational wave, and then also the Morse phases. And so that's the main information that we fold in. And then from the electromagnetic lens reconstruction, we look at the fluxes and the relative fluxes. And that's what the information that we fold into the joint analysis.
Okay, thank you very much. Any questions? Yeah, if not, yeah, let's finish. Thank you very much, Otto.
All right, thank you very much.
So we will have 30-minute break. So see you later. Thank you very much anyway. Okay, yeah, it's time. So the next speaker is Gaurav, and the title is Sifting for electromagnetic counterpart to the LIGO-Virgo-KAGRA Gravitational Wave triggers. So please start.
Hi everyone, I'm Gaurav Waratkar. I'm a PhD student at IIT Bombay, and I first want to thank all the organizers of Amaldi15, and it has been wonderful hearing from all around the world about all the nice work that has been going on in the field of gravitational waves. I am here to present the EM side of things, at least from the point of view of the prompt emission of EM counterparts. And I'm presenting this work where we have searched for EM counterparts for all the 90 gravitational wave triggers that have been published so far as from the previous observing run. I'm presenting this on the behalf of the CZTI team at IIT Bombay and IUCAA Pune. And here we go. So I just want to highlight one thing. Instead of sifting, we are calling this as CIFT. And I'll in my talk, I'll talk about what's the meaning of this CIFT that we have here. Here's a brief outline of my talk where I'll talk about the previous LVK runs and what has happened so far, and how our AstroSat's results like come into picture, and what's next for the field in general is what I will be focusing on. So just a recap, I'm sure a bunch of other talks have already covered this, but still a quick recap after the 30-minute break that we had is that we have these awesome gravitational wave detectors that have been online since 2015 when we had the first binary black hole merger, the 150914. This particular event was extremely important for the entire GW community, but in my talk I'll highlight how this is this has been very critical for the EM community as well, at least from the prompt emission side. And since 2015 there have been several observing runs. To be precise, there have been 3, and total of 90 gravitational wave triggers is what we have been detected. So in terms of EM counterparts, so how many have we seen so far? I can't really cover a multi-messenger talk without mentioning the most famous event that is important for EM community as well as the gravitational wave community, which was the gravitational wave 17/17, where about 1.7 seconds after the merger that was detected in the LIGO detectors, Fermi and Integral detected this significant emission in their X-ray detectors. And a few hours after that, the entire astronomy community pointed their telescopes and they found this kilonova that basically is one of the most well-studied event in the recent past. Apart from 17/17, has there anything else that we have had? So this was a binary neutron star merger, but let's come back to the first event that we had, which was a 150914. Now here, just after the first detection was triggered in the LIGO detectors, Fermi GBM detectors detected this 5 sigma event. This 5 sigma event in the detectors, and unfortunately, this was not something that was detected by other missions, and hence this still to this day remains as an unconfirmed detection that is related to GW 150914. What apart from this, there have been 9 candidate counterparts that were recently published in some optical follow-up that was published in a recent paper. And another interesting case was a FRB that was associated with a BNS event. So overall, you can see that all of these, a lot of, apart from the obvious 17/17, there have been a lot of other candidates that need follow-up and confirmation and further studies. So that is exactly where AstroSat comes in. And what exactly is AstroSat is what I'll talk about in this slide. So AstroSat-CZTI is one of the 5 astronomy payloads on board AstroSat, where CZTI stands for cadmium zinc telluride imager. It is an X-ray imager from 20 to 200 keV. You can see there are CZT detectors mounted on top of the V2 detectors. And when you talk about these higher energies, the assembly on top of these CZT detectors becomes increasingly transparent. And because of this instrument becomes an all-sky instrument and becomes sensitive to even off-axis bright sources, such as your GRBs. So in case you have an off-axis or an on-axis GRB, you notice a spike in your count rate, which we term as the prompt emission from GRBs. And in cases where you actually don't have any measurable change, then you can actually estimate the upper limits for that particular transient based on the noise levels that you have in your data. So since its launch of AstroSat in October 2015, in the past almost close to 8 years, we have detected 570 GRBs, which is close to 70 GRBs in a year, which is very close to what Swift-BAT detects on board every year. But more than that, I want to highlight this one point where we have over 50 new discoveries that we have done in the past 8 years. These 50 new GRBs are some things that we have. We are the only mission that have detected these GRBs, or we were the first ones to report that. For example, just a few months back, we had this very bright GRB on 9th March 2023, which was later discovered to be also detected by some other missions. All in all, the very high ratio of our discovery rate, almost 1 in 10, makes us understand that there is a high need for these coincident searches, at least in terms of the LVK triggers that we have, and there are good chances that we will be finding something, and we are highly hopeful of that. So in order for that to happen, we have made this new pipeline, and that's why we come back to the first point that I said in my at the start of the talk, which was CIFT, SIFT, which stands for CZTI Interface for Fast Transients. This is an interface and a standalone package that we have built for all things related to fast transients, be it FRBs, be it GRBs or LVK counterparts, and so on. So if you have a LVK trigger, we have this entire pipeline that takes in the parameters that are relevant and downloads the data from the relevant servers, and then generates the light curves, which a human scanner can then look at and classify it as a counterpart. If we get lucky, if we don't, then it can calculate the flux limits, which are weighted over the entire sky map that is visible to AstroSat at that particular time instant. So what we did was we took this Sift database and we ran it over the entire catalog that is public. And for example, this is one sample event that I wanted to just show here, which was GW191219, and it was detected in all three events. You can see the sky map. But in terms of AstroSat, how much we detected it, we did not detect anything. And the non-Earth filtered sky coverage for us was about 54%. And if you weight the entire flux limits for all the sky map that was visible, the visible sky map was this part, which is the shaded part. We got these flux limits. So we repeated this, like I said, for all the events that were visible for AstroSat, and we got something that is shown on your left-hand side for all the events where AstroSat was not in the South Atlantic anomaly, where whenever AstroSat enters this particular region over the South Atlantic Ocean, we switch off the detectors, and that's why we don't have any information for those events. But apart from those, we have 74 events for which you can see our X-ray prompt emission upper limit for this. Now, we can understand that this is happening once. We just wanted to understand how is it likely that it will happen 70 times. So we just took one random event. So for example, let's take the case of 1706-08, where we took one given luminosity, and let's say 10 to the power 48, and at that given luminosity, we took one line of sight in the sky map that was visible to AstroSat. So along that line of sight, we calculated the probability of us detecting a source which is at that luminosity, given AstroSat sensitivity, and we then just added up all of those values for the entire sky map that was visible, and which gave us these probabilities. So you can see that this will saturate along the coverage, that the maximum coverage of AstroSat for that particular sky map. And then we basically integrated this over all the 70 events that we have seen, more than 70 events. So if you just combine all of these, then you get a combined non-detection probability. And you can see that a bunch of events had very small coverage, but we have just placed a cutoff of at least 1% coverage. And you can see how this has nicely evolved into a combined non-detection probability. Now, what does this mean? This actually means that if you have a GW150914 GBM type of event type luminosity for all of these events, then it is completely ruled out. And this is one of the nice things that we get from non-detections, is that you can actually make use of this. So this tells us overall that if you had this particular event like GPM luminosity, then you wouldn't see it. But what about the individual events? So for that, what we did was we evaluated the possible emission models from binary black holes. And we targeted binary black holes because BBHS are the majority of the catalog events that we have from LVK. So we take an emission model. We import a lot of these physical properties from the posterior samples that we get from the catalog, and then we derive a free parameter that is from the GBM detection of 150914, just in order to understand whether that was a feasible detection or not. And then we repeat that for different inclination of the systems. and the three models that we are using are based on this analysis that was a very similar analysis that is done in Veres et al. 2019, and there are these three models. So how are these models working for us? So if we just take the example of neutrino annihilation model, there we expect that based on the posterior distribution, our flux limits, you can see that our flux limits are sensitive enough that had this model actually been in work, then we would have seen the actual detection from this event. So we repeat this for the other two events as well. So the other two models, and you can see that for some of the models, you can completely rule out these, some of the events, you can completely rule out these models. But for some models, you can't really do so. So I'm just showing you one of the events out of the 70 that we have seen, and these are some of our best events. So one might ask that how typical is how do you see it typically? So in general, the kind of the fluxes that we expect because of these three models are these. And you can see our flux limits are quite far to the right hand side, and because of which we either need a better flux limits model, which is a work in progress for us, but it is not expected to push it back so far beyond to even cause any damage to this. So what we need is probably a more sensitive detector. But that is not where the entire story ends. You also need detectors which are not hiding behind us. So for example, for 170817, AstroSat did not detect this short GRB because we were hiding behind Earth. And out of the 90 events, there are 16 for which AstroSat is in SA. So are we playing in small number statistics? One might argue about that, like 16 events is a very small number. You can't really generalize over it. So we just went ahead and looked at GRBs. So the same picture you can see at GRBs as well, that only 1/4 of the GRBs that were seen since AstroSat was launched, we have seen that. So in order to get hold of these three shares, which is not bright enough, we are in SA or we are either occulted, we need a more sensitive and all sky X-ray monitor. So I'll take one last minute to introduce to you Daksha, which is a low Earth orbit twin satellite mission proposed to Indian Space Research Organization, and it is a joint venture by these 5 institutes, and it is a extremely broadband, extremely high effective area, which will comprise of 2 satellites, which will give us near uniform 85% coverage of the sky. But for this community, the most important case here is that we will have about 11 joint detections every year. So you can see, as compared to Swift, the likes of Swift and Fermi, Daksha is doing much better, and it is expected to detect 9 times more gravitational wave events than the likes of BAT, for example. So that just puts into a category where there is no comparable EMGW or GRB mission that is coming up in the next decade. And you can find all of these papers about the capabilities of Daksha at this website, or you can go on to archive and look at the papers that are already on archive so far. So with that, I'll take last 10 seconds to summarize what we have done so far. There have been 90 LIGO-Virgo triggers since 2015, out of which AstroSat was not in SA for 74. And unfortunately, we did not see any counterparts, but non-detections can tell us a lot, and that is what my work has been about. For example, in 170817, we contributed to the SkyMap reduction because of our non-detection. And because of these upper limits, we are trying to constrain these binary black hole merger models. And I did not cover this part in my talk today, but automated O4 searches for all the significant as well as insignificant triggers, public triggers from LIGO-Virgo-KAGRA collaborations are ongoing. And solve the what's next for this field. We are hoping that Daksha will solve a lot of the problems that the EM community faces right now. And you can reach out to me for any questions on Oxford platform or to my email ID or anywhere else. But I'll stop now to take questions.
Thank you very much. So any questions? Yeah, please unmute and speak up. Okay. So yeah, I have a question from myself. So you made an analysis for the 70 events, but they have two different properties, like distance and the mass of the black hole. So how did you convert it to the combined analysis? Do you have any way? And
yes,
is it dependent on the model, or each model has the same dependence?
Yeah. So what we did was we took these, like I covered in this particular slide. We took all the parameters that are possible for that particular gravitational wave event from the posterior samples that we have, and we just left one free parameter for that was imported from the Fermi GBM detection that was corresponding to 150914, and based on this, we were able to sort of evaluate all different events. For example, this is one such event, and it is completely dependent on the physical properties of the posterior samples that we have for that particular event. And you can see that this was for 151226. And in my next slide, I had shown another such event, which was I don't have the name here, but it was for some other event. So all the physical properties are included in the model that we are, or the three models that we are evaluating. So that way we sort of integrate the distance, the chirp masses, and the spins and so on of that particular event.
Okay, thank you very much. Yeah, so that's why the histogram has a different shape for each model. Yeah, I understand. Thank you very much. Any other questions? Yeah. If not, let's go ahead. Thank you very much.
All right, thank you.
So the final speaker of this session is Jessica, and the title is BOBcat, a catalog of supermassive black hole binary candidates.
So
yeah.
I'll go ahead and start. So thank you. I am Jessica Sydnor. I am a graduate student at West Virginia University, working with Dr. Sarah Burke-Spolaor, as well as many undergrads at WVU to create BOBcat, a catalog of supermassive black hole binary candidates. And before I get into what is BOBcat, I briefly want to talk about why BOBcat is hopefully going to be very useful for the future. We're very much in the era of multi-messenger searches. I mean, I don't need to really preach too much as we are in the Multimessenger Astrophysics session, but we can learn a lot about supermassive black hole binary candidates if we look at them in both the electromagnetic spectrum as well as the gravitational wave spectrum. And so having this kind of up-to-date list of all of the different types of observations and all of the different studies that have been done in both spectrums on all of the candidates and sources out there is hopefully going to help aid us in the future as we start really working towards and doing mainly multi-messenger studies. And BOBcat will hopefully be a tool that will really help push forward this field. And there have been several studies that have already been done where when we take this multi-messenger view and we include electromagnetic information in our searches for continuous gravitational waves, we can have them end up being less computationally expensive. We can get some better limits as well as have better detection prospects in all-sky searches for pulsar timing arrays. So we're really definitely moving forward to needing to have this multi-messenger view. There's a lot of information about supermassive black hole binary candidates in all ranges of the electromagnetic spectrum. And there's been a lot of studies and a lot of different data techniques and analyses that have been done. And we're starting to now have that same wealth of information when we look at them in the gravitational wave spectrum. So having BOBcat collect all of this information and put it into one place is hopefully going to be very useful for this field. And I do believe that for the majority of people to kind of agree that a possible binary black hole candidate is actually truly a real binary, we're going to have evidence of that in both the electromagnetic as well as the gravitational wave spectrums. And so that is where we're hoping BOBcat is going to come into play. BOBcat is Black Holes Orbiting Black Holes catalog. It's a searchable public use database of all of the supermassive black hole binary candidates that have been published in the literature. So there is a literature review associated with the overall creation of this database. And we are going to have a lot of different queryable information so that you can create your own subset of these candidates to do your own studies on or gather more information about. And we're hoping to have queryable information such as location, the different redshifts, all of the different proposed binary signatures and the proposed binary models, along with the associated binary binary parameters for those models. And we're hoping that BOBcat will be a tool that will serve two communities, or maybe I should say one community, the multi-messenger community, but we really want to help aid gravitational wave searchers and modelers, as well as the electromagnetic black hole hunters that are out there and would like to have all of this information easily accessible. And what would be specifically included within BOBcat is two overarching general classes of information. We have some information that is going to be per candidate or per source. That is information that's not going to change depending on what wavelength you're looking at this source. It's not going to change depending on your data analysis techniques. And that would be things such as location, redshift, links to different databases if you want more information about the galaxy that hosts this possible binary system, just very overarching general information. And then each candidate or source is going to have at least one model, and that is where possibly different data analysis techniques can lead to slightly different binary parameters. And so most likely each paper about a specific candidate or source will become its own model, and that will have different parameters such as trip mass, mass ratio, the different orbital geometry parameters such as eccentricity, and we're also going to include currently derived parameters such as gravitational wave frequency and gravitational wave strain. And I say that they're going to be currently derived parameters because hopefully eventually as the gravitational wave spectrum becomes a lot more probed with all of these really great surveys and up and coming surveys and telescopes and such, those will eventually become observed parameters and not just derived parameters. So we are very much hoping to include all of the different spectrum, all of the different information, and house it in one location. This is a very kind of step back overview of what BOBcat looks like. And on the left-hand side, we do have our front end of BOBcat, which is our user interface, the web page, where you can search through our database. There will be some interactive plots that might be useful, really the front end and what people will see when you use BOBcat as a tool. And then on the right-hand side, or the majority of the slide, is our back end for BOBcat. And if we look all the way towards the right hand, we have our published literature candidate and models, and that's our literature review that we're currently doing, as well as we have these auto brokers, which are some future goals that we're hoping to have in BOBcat. We would really love to have some auto brokers for surveys such as ZTF or LSST, because they are most likely going to start finding candidates at a very fast pace, which might be a little cruel to have a student have to ingest all of those sources into BOBcat. So having something that's automated would be very useful. But again, that is a future goal. And currently we are just focused on our literature review. So we're taking the information from the literature, from the papers, and putting them within our different classes. We have a source class that's going to have that general overarching information such as location and redshift. And then we have model classes, which is that more specific binary model parameters such as chirp mass or eccentricity and such. And we are having those kind of then go into our ingestion script where we clean, calculate, and fill parameters. And the calculate and fill parameters kind of goes back to our BOBcat utilities, which has been this library module that we're going to release in addition to BOBcat that kind of just organically grew out of us trying to fill in as much information as we can. It is a bunch of calculations and functions that allow you to process the different parameters within our source and model classes. And that's really just because when you look at a paper, you're most likely going to get just a few numbers, a few parameters, but you can get more information by doing some calculations. And so we want BOBcat to be filled in as much as possible. So we will be doing those calculations, but clearly stating which values we are calculating. And so once we fill in as much as we can, we then format it and move it into our actual database. We're using a Postgres database, and that is our true BOBcat, our true catalog, and that is what is going to be connected to our front end for when you do all of your different queries. So all of this currently is up and running in a skeleton type of sense. We have everything working and connected, but we are going through making sure everything has all the functionality that we want and is hopefully easy to read and can grow easily. And as a more detailed current status of BOBcat, we have about 800 candidates in our offline version. We are very diligently going through these and trying to get them into our database itself. We have also created some small beta versions that we trialed with some very close collaborators, such as the one that you see on this slide, BOBcat beta version 0.0. This is very much just so we could get an idea of what people would like to see in a web page for BOBcat, as web page building is not necessarily a strength in many of our collaborators that we are learning, and we are working towards having that be a useful web page. And also, I am but one single person to think of all the different user input that could possibly go through our search functions and search boxes. So those have been very useful to kind of help me make sure that I am accounting for everything. And we are working towards an official beta release in the fall of 2023. So this coming fall, just a few months away. And we're really working hard to make that happen. And we should be able to hit that goal. And you might be wondering why I'm talking about BOBcat if it's not necessarily available right now. And the biggest thing is that we would really love to hear how you would use BOBcat. This would allow us to make sure that the functionality and the flow of the web page is going to be the most useful to the most amount of people, as well as making sure that we're accounting for all of the different information that people want to see within BOBcat. So if you could maybe envision yourself sitting down to start a project or maybe write a proposal and you think that BOBcat would help aid your research, if you could maybe, open up an email and explain in a few sentences how BOBcat might fit in with your fit into the scope of your project, and you want to send that email to me, that would be really, really fantastic. We're very much interested in seeing how people would use this tool in their research. And an example of a specific use case would be using BOBcat in targeted continuous wave searches in pulsar timing arrays. There's been some work done in Arzimane et al. 2020, which was led by Caitlin Witt, where they took the electromagnetic information about several parameters to derive the priors when they did a targeted continuous gravitational wave search. And that ended up giving them an upper limit of a chirp mass for 3C66b that was several factors better than those found when you just did kind of blind searches and PTAs. And so it's a very interesting way and useful way to start looking at binary black hole systems in this multi-messenger view. And so BOBcat would be able to aid this research because it would allow easy access to those binary parameters for the different targeted searches people might want to do, which is very exciting. If we look on the plot on the bottom left, we have gravitational wave frequency on the x-axis and strain on the y-axis. These shaded regions and boxes, those are the expected or predicted ranges for several different types of candidates within BOBcat. And we've put over some slightly outdated now PTA sensitivity curves, as well as the dotted line, which is our future sensitivity, hopeful future sensitivity with SKA and the full IPTA. And you can see that PTA sensitivity is very much reaching the range where hopefully we'll be able to detect a signal from these binary systems. And so BOBcat would be a very useful tool to help aid these targeted searches. And just very quickly, what's next for BOBcat? In the near future, like I said, we will be releasing BOBcat beta version 1 for official beta testing only. It won't necessarily be public, but we're going to be doing that in the fall of this year. And then future goals, we're going to have a public release, obviously, as soon as we can, that will have the base functionality searches, as well as some interactive plot functionalities. And far future goals, we would very much like to integrate some PTA time to detection into BOBcat, hopefully those auto brokers, as well as thinking about potentially expanding BOBcat to include maybe wider separation sources or recoil candidates or other black hole binary candidates that would benefit from having all of their information within one single place that is easy to find and easy to use. And with that, I'll leave this slide up and have one final plea that if you have a specific use case that you think would be great for BOBcat and would be a useful place to use BOBcat, please do let me know. And with that, I'm happy to take any questions or comments. Thank you.
Thank you very much. So we already have a question. So Heinz?
Yeah, I was wondering why you're not letting other services host your catalog and have your own web interface like this year. Or...
Are you saying, oh, I see what you're saying. So we have briefly thought about going that route. Initially, we didn't want to do that to help, we didn't want to go that route because initially we didn't have that many candidates and weren't thinking about how much BOBcat might grow. But as we have started to kind of dig deeper into building BOBcat and looking future forward with BOBcat and how much it might grow and how many people might want to use it and such, we have started looking into that to see if that would be a better way to kind of do it, though we're have at least a beta version of BOBcat that has already been built, and so we're just going to move forward with that. But we have started thinking about maybe that would be a better way and a better use of our time.
Thank you.
Thank you very much. So our next question by Hippolyte.
Yeah, so thank you for the talk. I hope you can hear me. I was wondering how you link or how you are estimating the binary period from the light curve's periodicity of your observation. If you,
I'm sorry, could you repeat the question? How we link?
Yeah, you said you could estimate the binary period from your observation. So, for example, from a light curve, I suppose. So, how are you doing that?
Yeah, so we are only calculating something like orbital period if enough information and parameters have been included in a specific paper that we can use some of the equations that are out there. But if we aren't looking at light curves ourselves and using some kind of like Lumsgargle to get a period from that, it would depend on the paper that we're kind of gathering this information from. If they have a light curve and they get an orbital period from the light curve, we will note how they got that light curve, or sorry, that period from the light curve. So that information will be within BOBcat, but we are not doing it. We're just gathering that from the papers.
Okay, I see. Thank you.
So any other question? We have 2 minutes or something. Yeah, if not, yeah, let's close the session today. Thank you very much. So thank you all the speakers for great presentation and also keeping time. And also for the audience, thank you very much for the great discussions. Thank you very much.